Right. Hello, everyone. My name is Karthik Drisami. I'm a faculty member in the University of Michigan, and I'm going to be talking about some new ideas that we've been working on regarding the construction of data-driven models of complex physics over complex geometries. Really, I'm going to introduce two concepts, which I hope you'll find to be very interesting and useful, even if you don't fancy how exactly we use these concepts. Okay, so that's the general idea. Okay. And before I start, obviously, most of the credit, if not all of the credit, goes to my students who did most of the work that I'm going to be talking about. So James Duvall is a current PhD student, and Shaowu and David just very recently graduated. All right, so let me start by relaying the motivation for the research that I'm going to present. First of all, we're interested in constructing effective data-driven models of complex physics over complex geometries. As I mentioned, as an example, I'm showing flow over a gas turbine combustor. It's turbulent, chaotic, multi-scale. There's a lot going on. That's complex physics. And of course, the geometries involved in this computation is also complex, right? So you have different elements on an unstructured mesh with various kinds of scales, right? So that's one of the challenges. And the other main qualifier is that many of the changes in these problems occur in a non-parametric way, okay? And as an example of what I mean by non-parametric, here is a mesh of the flow over an automobile. And of course, if we change this to a completely different automobile, or even if it's a variant of this automobile, you can imagine that you cannot describe the changes in a continuously parametric way, right? So the mesh may have to completely change. You may go from 10 million elements to 11 million elements with a different graph structure, etc., right? So that's what I mean by mesh topology change. And of course, the other challenge is learning from unit or subsystem problems and then predicting over a complex system. And for that, let me introduce to you some of the work that we're doing with rocket combustors, right? So the challenge here is the full system is impossible to simulate with high fidelity. So we just have data corresponding to, say, one injector of the rocket combustor. Now, can we take these trained models and put them together to model a combustor with, say, 3 injectors or 5 injectors or 7 injectors or many injectors in a different form, right? So that's some of the challenges that we want to address today, right? So again, just to summarize, non-parametric changes, unstructured meshes, mesh topology changes, and some kind of geometry agnostic predictions, right? So that's the motivation for our work. And before I jump in to what, the main topic of the day, I want to talk about the kind of things we were doing, say, a couple of years ago, right? So, and if you're interested in modeling spatio-temporal fields, we were heavily using the concept of convolutional layers. And by now, everyone knows what convolutional layers and convolutional neural networks are, but we use it in a certain way. So let's say you have a 2D problem represented on a Cartesian mesh as a schematic, right? So this block would correspond to, say, pressure or one variable over the mesh, right? And you could have multiple variables or channels. So you could have multiple blocks, and all of this corresponds to one time instant. Okay, so you could have multiple time instants that are shown here. So what we can do then is to use spatial encoding using convolutional neural networks to take each of these slabs and convert them to pencils, right? So each of these pencils contains a compressed version of information in all of these variables at that particular time instance. So that's spatial compression. And then you can take each of those pencils, which correspond to a spatial compression, and then apply temporal compression by a temporal convolutional autoencoder. So that's similar to spatial convolutions, except there is a time dependence or a directionality associated with it. So then you have achieved compression space and time, and you have this vector of latent variables. And then we take those vector of latent variables And then if you have some global parameters in the problem, you can use regression in that latent space. Okay, so that would be basically compression. And then if we want to make predictions, we would start with the parameter and then we would follow this red arrow, right? So this is the kind of thing we were doing. And just to highlight one example of the kind of applications we were tackling earlier. So this is fairly complex, I would say. So this is flow over a ship. And the challenge here is to predict the transient flow, okay? So the ship is moving in a certain direction and it already has some complex vortex shedding, etc. And then the wind suddenly changes direction. So you want to predict how the flow topology changes instantaneously. So it's a transient prediction. And as you can imagine, the vortex dynamics can get fairly complicated. But we were able to do that fairly well, I would say. I mean, in fact, I would say very well, because this was among the first times we were pursuing purely data-driven models instead of a more physics-based model like a projection-based ROM. And you can find more details in the paper, but what I want to impress upon you is we were able to, I mean, given enough data, of course, we could make good predictions in future state as well as in as a function of parameters. And these were almost as good, if not better, than some of the projection-based reduced order models that we're comparing them with. Okay. So in summary, it was successful. And to me, it just gave me the idea that, okay, we can use these data-driven models for some serious problems. But what I'm going to talk about today is the extension of that, right? So we want to go well beyond that. First, everything that I showed you earlier was on structured meshes, right? So even if you have a complex mesh like the ship airwake, this could be decomposed into a bunch of multi-block meshes, right? And the second is, as I mentioned earlier, the mesh topology could change. And to impress upon you what that means, so here is some problem. Think of it as a Poisson equation, and there is some kind of a domain with some boundary conditions. So can you learn from a domain like this and from a domain like this, and can you make a prediction in a domain like this, right? So this is this is not the case where the mesh topology changes dramatically, but there's a problem where the mesh changes, right? So you have these objects sitting in different locations and they may have different characteristics associated with it. And then you're trying to make predictions on a mesh that has, different set of points, right? So this is a problem where you can't apply CNNs directly. In fact, the first thing we tried was we went to a graph convolution neural network because you cannot deal with Euclidean data anymore. And that kind of worked for us when we use spectral convolutions. But the fundamental problem was that, as I showed in the car geometry earlier, if the mesh topology and the mesh completely changes, you have to throw away what you had learned earlier, right? So that's why we want to move away from it. And I also mentioned the idea of learning from simple or subsystem problems and then predicting on more complex problems, okay? So the two ideas that we'll pursue today, one is called the nonlinear independent dual system. I'm going to introduce that in a couple of minutes. And then the idea of conditionally parameterized graph networks. And I mean, it's these days, I do want to say that it's very hard to argue that nothing is really new, especially when you're doing machine learning. So I would admit that our work is inspired by several recent developments. I've listed a few here. And if I had more time, I would talk about each of these and connect them very properly to our ideas. But I'll let you explore these papers in your own time. But I do want to say that most of these come from a different field like computer graphics. And then we take those ideas and then we adapt them in a suitable way to solve the problems that we're interested in. It's okay. All right, let's move to the first part. So I do want to say that ultimately what we want to do is to make predictions in a continuous field, right? At least in the first part of what I'm going to talk about today. So you should not be restricted to a particular mesh because A, your data can come from meshes that have different structure. And B, you want to make predictions in a mesh-agnostic way. Okay, so we want to have continuous representation of the flow field variables, which is not based on discrete snapshots, as I mentioned earlier. And we also want to make field predictions over multiple variables simultaneously. And of course, I spoke at length about mesh geometry and topology changes. Okay, so the key idea that we start with is the idea of implicit neural representations. It's a terminology, and maybe you could even say the idea comes from computer graphics. And some of these papers listed here have some good information that that you might find pretty interesting as well. But the idea is that many problems can be cast in this form. You have some set of implicit relations, f, x could be a state variable, and what you want to model, your phi of x, can be represented implicitly by this set of relations. Okay, so the idea is to have a neural network to parameterize this variable phi. And of course, in addition to phi, you may have multiple derivatives of phi as well in a physics-informed neural network kind of way, right? So an example would be a sign distance function neural network, which has been used quite a lot over the past couple of years to basically compress an object's geometry representation. Okay, so what is a sign distance function? It's, in simple terms, it's basically the distance to the closest point, okay, on the surface. Let's say you have an object like an airfoil or a hexagon. A sign distance function would just be the distance to the nearest wall. Okay, so it would take a value of 0 on the wall of the object, and then it would take a positive value in the interior of the domain, and it would take a negative value inside the domain, that inside the geometry. Okay, so it's really a sign distance function. And moving forward, when I use the symbol x prime, I mean it's a concatenation of the spatial coordinate, right? In this case, if it's 2D, you have two variables in this x, and then phi is basically the sign distance function corresponding to the point that you're interested in. Okay, so that's I call this the augmented vector x prime. Okay, so that's the general idea, and I want to mention that there's a big difference between what I was showing earlier and what we're doing now, right? Earlier, we were feeding the entire mesh as an input, right, to the CNN, whereas now we're working with point-wise inputs, and that by itself is a pretty significant idea. Okay, so, and it sounds kind of trivial, but it took us quite a bit of time to get to this mode of thinking. And given we have this mode of point-wise thinking, let's see what is the simplest thing we can do. Okay, the simplest thing we can do is we can take the augmented vector, right? This is the spatial coordinates and the sign distance function. And here is, you may have some global parameters. You concatenate them in a vector and you throw it into a neural network. And the neural network, of course, has some weights. I'm calling it as theta m. And then you can try to make point-wise predictions of the output. Okay, so I call it design variable MLP. Again, it's pretty simplistic, and it can give us some reasonable results. But of course, you can't expect it to do wonders, because it would maybe try to memorize the entire flow field point-wise, and you may need a lot of data. It has some drawbacks, some pros and cons, and I'll leave it at that. Okay, so now a more powerful idea is what we call as the design variable hypernetwork. And the idea is you're basically separating the two types of inputs. So here is your augmented state. And then we have an additional hypernetwork that generates all of the weights and biases of the main network, right? So that's why it's called a hypernetwork. So now, if you just think of this neural network, this hypernetwork is basically parameterizing the weights of the main network, and they're related by. So here are how the two networks are related. So the hypernetwork takes the global parameters and then builds the weights, and then the additional network basically uses the weights. So that's the general idea. And then we have the idea of NIDS, which is nonlinear independent dual system, where it's a variant of the DV, the design variable hypernetwork, with the idea that only the weights and biases of the linear output layer are parameterized by the second networks, right? So you have, again, a main network and a parameter network, and the weights are parameterized by this parameter network. And if you want to think about it from an interpretability standpoint, you can, because the last layer of the neural network is linear, the last network of the parameter network of the main network is linear, you can think of this as some kind of a POD that has a continuous representation in space, right? Because now you're not stuck to the discrete mesh points, which defines your problem, but rather you've created a continuous field of modes, and then you're combining each of those modes in a linear fashion. Okay, so now I'm putting all of these three things together. The design variable multi-layer perceptron, where there's only one network and you throw everything in as an input. And you have the DVHnet, which has a hypernetwork that supplies the weights, and then the NIDS, which is a variant that just supplies the weights of the last layer. Okay, so that's how this is structured. And in the following, I will fix that all the main network architecture is fixed among all three methods. So that makes it a little hard to compare because the number of parameters in the problem are different. But again, you can refer the paper for more detailed tests. So here is the first problem, the Poisson problem that I kind of introduced earlier. So you have a Poisson equation with a certain type of boundary term. And then you have basically a Dirichlet boundary condition on the internal and external boundaries. So again, the challenge here is you have a bunch of shapes. I think you have a total of 9 different shapes going from circle to triangle to hexagon, octagon, etc. And of course, the radius of each of these shapes can be different. The shapes can be rotated in some kind of arbitrary way. They can be centered in some kind of arbitrary way. So there are these different parameters. And of course, rotation does not mean anything for a cylinder, but it means something for these other shapes. So a bunch of different shapes that can be located anywhere on the grid. And then there is a Poisson equation sitting on top of it. And we want to make predictions on unseen geometries and on unseen grids, right? That's the challenge. And again, here are some of the predictions. Again, these are for, I don't even think an octagon was part of the training set. And then you can have, so here is showing one particular prediction for an octagon. Here is the ground truth, and here are the three different ways in which you can cast the pointwise network. And here is again the prediction for another shape. Again, for the first case, the errors are very small, as you can see, maybe 0.1%. Whereas for the triangle, which is the hardest object because the sign distance function is not a perfect descriptor, the error is more of the order of 1%. But again, however fine or coarse you make the mesh, because our output is pointwise, you can still make predictions. Okay, so here are some other metrics for different shapes. And as I did mention, the triangle is harder to process than the others because it's very dissimilar compared to the other problems. But again, so you can refer the paper for more results. Again, quickly, I want the focus to be on the concepts rather than the results, but I will at least quickly run through another set of results. So this is actually the problem that motivated the entire work, because General Motors came to us and wanted to make flow field predictions over different geometries. And we said yes. And we initially thought they were parameterized, but they ended up, the meshes tended to be very non-parametric. So again, the goal here is to have some data sets, some data snapshots on certain geometries, and then try to make predictions on other geometries. And again, I'll let you refer the paper for how good these predictions are, but again, it was able to do the job, right? So again, the key thing is the mesh can change in an arbitrary way, and we should be able to handle that. And more or less, in all the cases, the design variable hypernetwork worked the best relatively. I will skip these airfoil flow problems again. All right, so what is the interim summary of what I have spoken about so far? Right, so we trained surrogate models on unseen meshes, mesh topologies, and geometries. And it introduced to you 3 different ways in which we can do point-wise inputs. And I do want to bring to your attention the fact that because these inputs are point-wise, they require orders of magnitude less memory than convolutional neural networks, right? Because in CNNs, the entire mesh is an input. And you can imagine things can get very, very quickly out of hand if you go to 3D. So that's why most applications of CNNs, first of all, are on 2D. And even the few applications in 3D are very limited in scale. So I doubt anyone has more than a 128 cube CNN. So anyway, so we had a task, we had a problem, which is, as I mentioned, continuous predictions on unseen meshes, topologies, and geometries, and we have a technique that does it. Okay, so now the question is, can we do better and more interesting things? And for that, I introduced to you the idea of conditional parameterization. Again, I cannot argue that, I will not argue that we have completely come up with this idea of conditional parameterization, but we've taken this idea and we've applied it and adapted it to different classes of problems in a paper that I'll soon cite. So again, the first problem with some of the deep learning models, at least the naive ones that we start with, is we kind of do a brute force fitting, and we don't concatenate different type of heterogeneous features like graph nodes and edge features, etc. Right? So far, we just take data points as data points. We don't give enough importance to. We did not give enough importance to the fact that there's an underlying mesh topology and certain nodes are connected with others for a certain reason. Okay, so the idea of conditional parameterization is to use trainable functions of input parameters to generate the weights. And I'll give you a simple example. Okay, so typically, if you have a standard dense layer in a neural network, right? So this is, so you have you as your input, you have your weight and your bias, and you typically combine this, in this kind of way: activation function, weights, biases, inputs. And the issue here is that typically this weights and biases are independent of any inputs in the prediction stage. And so that is not the best thing we can do, especially if we know a lot about the problem, right? So let's say here is our neural network, so to speak. And the function that I'm hoping to approximate is actually h squared, right? H is the input. So I could obviously use a bunch of nodes and try to fit this function h squared and hope to make predictions. Or what if I make this w also as a parameter, and if I learn this w to be h, then all I would need is just a single neuron that has w equal to h, the bias to be 0, and a linear activation, right? So So that will be a much more efficient way of fitting h squared than just brute forcing it, right? So this is obviously a super simple idea. That what we're going to do is basically trying to generalize this, and a lot of detail is in this paper. So it's a NIPS paper from last year. Okay, so the idea is, as I said, introduce a parameter that's a trainable. Basically make the weights trainable, right? That's the simplest way to think about it. So again, U were your inputs, B were your biases, and then instead of the weights, you could have basically a trainable function. And the simplest way to visualize this is, to represent this trainable function itself as a neural network. But the key thing is you're basically injecting these parameters, right? And the parameters could be a function of the inputs as well, right? So earlier I just showed you that I made the parameter to be equal to the input, so I could model h squared, right? So that's what I mean by you can model high order terms. And then when we come to these learning PDE solutions or representing PDE solutions, you know that we can represent edges and we can represent boundary features, and all of those can come in, but I'll explain that in the next couple of slides. So here is an illustrative problem. This is, again, just to impress upon you the point. So let's say I have a 2D advection diffusion equation, right? And I want to I have some snapshots of this, in fact, data at some points, at some times, and I want to basically build a data-driven model that's generalizable for the PDE. So here I use a very simple, so again, if you were to discretize this using finite difference scheme, you would have some kind of a numerical scheme like this. So the only thing that I'm doing is I am specifying the CFL number delta t over delta x times h, and the diffusion number nu delta t over delta x squared. So these are my parameters, right? So I introduce the parameter in this form. And by doing that, I can basically learn the PDE to represent any kind of arbitrary initial conditions. Okay, so here is this advection diffusion problem. So this is the initial condition. This is a particular initial condition. And then time evolves. And of course, there is some advection and diffusion. So if I use the approach that I mentioned earlier with these sets of parameters, parameterized weights to be more precise, I can do really well. Okay, I can beat out the POD, a convolutional autoencoder, and I can do as well as a CNN, but with less parameters. Okay, so you can see more in the paper. So now, okay, so that is an idea now, and we took a simple linear problem and we're able to show that we can not only fit what we see, but also basically recreate the entire PDE by feeding the neural network a conditional parameter based on our physical knowledge of the problem. Okay. So now how do we take this and make it work for much more complex problems? So we propose what is called conditionally parameterized graph network. And again, we break away from the fact that CNNs can only work with Euclidean data. Of course, you can have graph networks, but then they're sensitive to topology changes too. So what we do is we take a look at, say, an unstructured mesh. So this is just definitions. Of course, you have nodes, and then you have cell centroids, and then you have your mesh edges, and you can also have these dual edges. So all of these is information that's available once you have a mesh, right? So, but we'll make these as features, right? So this E would be an edge feature, for instance, right? And what we want to do is basically build a model that takes, say, the inputs at one time step, and you basically march it one time step forward. Okay, but we want to do it on unseen meshes. right? So it's not like there is an underlying mesh structure. So we basically want to learn the solution operator, but we want to do so in a way that you can train in some meshes and make predictions on different meshes, as long as the underlying physics is represented. Okay, so we basically cast this in the form of an encoder, processor, decoder. So let me just walk through the representation here, and I have two other figures to help impress upon the problem. Okay, so first we take the inputs at a certain time, and then we use two conditionally parameterized dense layers that basically take the inputs and then encode them, right? So basically reduce the dimensionality of the space of the state space. That's what the encoder does. And then so by doing this, we basically prepare the CPG net for high order interactions, just like I showed you in that simple example earlier. And if you have captured the right high order interaction, like in the H squared case, you have a purely generalizable model. Okay, so then the second step is a processing step, which does edge conditioned message passing. And what this really does is, just like if you have a, say, finite volume mesh between two adjacent nodes, there is a flux exchange, right? So that is what is being mimicked, but of course it acts on the encoded inputs. And then once the processing step has been completed, the decoder basically converts the hidden variables to the physical space, right? And in all of these cases, there is a conditionally parameterized network underpinning each of these layers. And maybe skip this and maybe jump in here, right? So this is how the mesh, how the network looks in practice. So in the encoding step, we have some node features that go in, and we have some edge features that go in. So we have these two inputs. And then in the processing step, both of those features are combined in a conditionally parameterized setting, right? So just see how the edge features and node features are concatenated. So this would, if you think of this as a flow calculation, so this step would do the flux exchanges and the source term calculations. And then the decoder basically takes everything back to the physical space that we're interested in. Okay, so that's the general idea. And I do want to mention a very, very important point. The training now happens at a cell by cell level. Okay, so if you have like this set of mesh points, then you can start training your encoder. So training your CPG net, it's kind of like you're basically learning the solution operator and the way the solution operator gets computed in a local setting, right? So you don't have to give it the entire mesh, and then you can just learn on, say, clouds of points. And again, a big difference in memory and processing compared to CNNs. So again, the NIPS paper has a lot of experiments, 7 or 8 experiments. Do make sure to check out the supplementary materials section of the paper as well. And here is an example where this is flow over a cylinder, which is a fairly simple example, but the two complicating factors are, one, the prediction goes after transients, and two, more importantly, you could maybe learn from a mesh that looks like this and a mesh that looks like this, where you have cylinders of different radius located at different locations and on different meshes, and you want to make predictions in geometries like this. Okay, so the mesh, you are going to be using different meshes. You could have different number of mesh points, different connectivities, maybe even slightly different topologies. And compared to another benchmark, the so-called mesh graph net, we are doing about as well as slightly better. And you can check out the paper for more details. All right. The last example I want to talk about is rocket combustion. Again, now things get very complex. There is turbulence, there is acoustics, there is reaction, and they all combine. And it's also an extremely stiff problem. And again, for this case, we're using a single element rocket combustor. So your oxidizer comes in here, your fuel comes in here, there is mixing, and there is burning, like I've shown in the previous slide. And again, you can look at the paper for all of these results, but even for this very hard problem, the CPGNet is able to make some good predictions for not just pressure and temperature, but also for other quantities, whereas the graph network, without the conditional parameterization, for the same kind of settings, it fails pretty miserably. In some cases, not all. And of course, if we use standard POD-based data-driven models, they cannot represent the underlying physics very well because there's a lot of convection, etc. Okay, I don't want to give you the impression that this entire problem has been solved, but it is giving us a very good baseline to start constructing models and to start making them predictive. All right, so in summary, for the second part, the idea of conditional parameterization, again, as I mentioned earlier, even if you don't quite want to do these things the way we've done them, simply the idea of conditional parameterization, the idea of making the input parameters, making the weights as functions of input parameters, I think is very powerful. And in the NIPS paper, not only did we show prediction experiments, we also showed how well we can do for problems like super resolution. Okay, so the idea of conditional parameterization is very significant, and people are using it in other contexts, in other areas. And what else do I want to say? Yeah, if you use direct conditional parameterization, I do want to mention that it causes a linear increase in the number of parameters in the problem. But then you can compensate that by reducing the number of latent variables you have, right? So those experiments are in the paper as well. And I feel that it has potential as a truly generalizable mesh-independent surrogate when you're talking about predictions. And you can also encode different types of boundary conditions by using ghost cells, etc. And of course, what are the things we're working on right now? So at least as I presented, it does not have explicit stability guarantees. So currently we are using some kind of evolve, filter, relax type of regularization approach for stabilization. And of course, with all of these models, there is a lot of uncertainty, lack of data, etc. So at least as a first step, we're using variational inference to address uncertainty. So that's all I have. And I want to summarize with the motivations, the techniques that we use, and of course, most importantly, some of the work that we built on. Okay, so I leave you with this. And if you have any questions, we can talk at any point. Thank you.